So now we're getting down to the last sort of functionalities of FreeRTOS, namely that there are software timers. Now the difference between a software timer and a hardware timer is that the hardware timer, the CPU's clock is sort of funneled, or not the CPU's clock, but the clock of the board is funneled separately, usually into a hardware timer when we're dealing with embedded systems or a microcontroller. And so these timers, they count externally to the CPU clock. The CPU doesn't actually increment any values or variables to count. It's done externally, offloading this counting work to this peripheral, this hardware peripheral. Now the difference with a software timer is that it's all done in software, meaning that there's actually a variable or a value stored in memory that the CPU is then responsible for clocking up. And so this means that there's an overhead incurred from the timer, and that generally they're used for sort of smaller user-based application things, but they wouldn't be used for instance, for generating a systic, because the overhead that you'd incur would be far too much. So FreeRTOS offers a real-time timer sort of functionality, meaning that you can invoke periodic actions, you can delay using timers, or you can do things, for instance, if you're making a game, you can do animations or what that happen with respect to time, these sort of things. So the functionality of them is quite simple, really, that you provide some sort of a callback, like a code, like a function, really, same as when you do a task, and this thing can be called at a certain point in time. It can be triggered once, or you can set it up to happen at regular points in time. So it sort of functions similarly to a task with a delay in it, in that you can sort of figure, hey, I want to run this code, but I want it to sort of happen so and so often, right? But it's quite easy. They're a bit easier to manage than tasks because they're a little lighter weight, really. So if we look through I don't have the API put in here, but I'll do an example of one in a second, and we'll see the API. It's really quite simple. But there's only like a couple more things that I need to talk about when it comes to FreeRTOS specifically. And one of the big issues is, or something that comes up quite often, is FreeRTOS's memory management. And so why it's different is that there is no direct malloc and free for dynamic memory allocation, mainly because when you're using sort of real-time embedded systems, you want to try and allocate everything as much as statically as much as possible, because static allocation is safer, right? Because you know when you compile your program how much memory is being used, and if, for instance, you're compiling a program that uses too much memory, usually the compiler is aware of the board you're compiling for, and it will then warn you, say, hey, this is going to take up too much memory, blah, blah, blah. You don't have any sort of unaccounted for memory usage problems when you compile everything statically, which is not always possible, but in the world of embedded systems, and especially in the world of sort of like real-time and safety-critical embedded systems, static allocation is the way to go. But when you do need dynamic allocation using a FreeRTOS system, you need to use the sort of memory management functions provided by FreeRTOS, because they provide a number of functionalities. Namely, the FreeRTOS comes with 5 different heap implementations. So we remember from memory management, talking in the C language, the heap is where the memory is dynamically allocated to using malloc, calloc, realloc, and is freed from using the free function. And so the heap implementations in FreeRTOS, as we can see here, there's 1, 2, 3, 4, 5. They offer more features, or don't offer features, essentially. They offer sort of flexibilities and complexities that you can then choose from as a user. What does your application need, blah, blah, blah. So we can sort of see here, heap 1 is very basic, and it doesn't really offer the possibility to free memory. So essentially everything you allocate is just allocated then permanently for the rest of the application's execution, essentially. There's then heap 2, which is slightly more complex. It allows you to free the memory, but the memory can be defragmented. And for those of you who are familiar with defragmentation, it means that the memory is not continuous, in that it doesn't reorder your memory to have it as a continuous block in memory, meaning that you can end up with really sort of memory allocations that are all over the place. And for small embedded systems without complex memory management implemented, then this can mean that at some point your memory management's really not going to know how to or where to allocate everything. So it can lead to a slowly degrading system in some applications. And so then heap 3 allows you to do essentially everything that you would normally except it just adds some thread safety to it. So it's sort of like a bit of a hacky wrap around the existing malloc and free functions. But then we get into heap 4 and heap 5, where we really have more advanced uses or implementations where the free RTOS has actually implemented defragmentation, and so it will allow you to better manage your memory, which is very important on extremely memory constrained devices. So just be aware that there are these implementations, but the most important thing to know is that when you're using free RTOS, you should always call these PV port malloc and PV port free, because they will wrap around the appropriate heap implementation. And if you use malloc and free, not so much on the emulator, but on an actual embedded system, you'll generally find, or often find, they don't work. Like the function, the memory pointers that you get back are usually null. Small other note then when it comes to free RTOS, in some of the examples I was modifying things in this file, but there is a file that ships always with free RTOS called free RTOS config.h, and it's found in, for instance, the emulator in the includes folder. And what it is it's essentially just a header file that's full of hash defines. And so CIF projects commonly use hash defines as a way for users to set flags on or off for when they're compiling. So if I wanted to use preemption, I define this config use preemption to have a value of 1, and somewhere, or well, not somewhere, but all over in the code where preemption is required, there'll be some sort of an if-def statement, which stands for if blah 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 is defined, or there'll be some preprocessor conditional statement, because a preprocessor can also evaluate if statements. It'll say if config use preemption, meaning it's not a non-zero value, and then it'll include the chunk of code that this if-def conditional statement actually surrounds. And so by doing this, you can sort of set and unset the properties, and you'll commonly see in the documentation if you're going through to look for a certain feature, like the blah 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 is only works if config something something is 1, all right? Similarly, there are also other values in here, such as the amount of priorities that you can use, and another important one is this tick rate. And so I set this really low for my examples, which means that the scheduler is not invoked very often, but this is not really very optimal. Usually in pretty much all applications I've worked on so far, about a millisecond tick rate is quite okay. It's sort of a nice compromise between responsiveness and overhead. And so this, here is a example of the preprocessor conditional. So this allows for you to then sort of include only the features that you need, and it will allow you then to reduce your binary size, because the code that you don't need is, if the preprocessor, or if the linker, for instance, might not link it, but the compiler, in the case of features that you don't need, the compiler excludes it because it's not actually included in the source. So some more general comments. I was mentioning, this configuration is done in FreeRTOS config. So every item, these are sort of things that people and students forget, is that you have these handles in Semaphore. You have, not in Semaphore, in FreeRTOS, handles for tasks, for semaphores, for queues. And so they need to be created before they're used. And I want to stress sort of the good way of doing this is that you set them to null at the top of your main function, or at the top of your main.c file. And then before you use them, you always check if they're not null, because if they're not null, it's mean they've been initialized, and so you won't run into the problem when you're getting really weird behavior when you're trying to use a queue that hasn't been initialized yet, and the queue's pointer is full of some random junk in memory, and therefore you're pointing to random stuff in memory and weird things happen. So by initializing them to null before you use them, and then checking that they're not null when you use them, guarantees that you are like for instance, you're not using uninitialized queues. But by doing so, you would also probably, the first time you do this, sort of get the return code and be like, why is my programming exiting with this return code? Oh yes, here I haven't initialized the queue I'm using. And so it'll sort of help you to catch these little things that you need to implement quicker, right? So there's also a lot of, which we didn't talk about when we talked about the APIs, is that there's these functions for like a lot of standard things using queues, using semaphores, and they all have from ISR written, like appended to the name. Now what this stands for is that they should be used in interrupt service routines. And so this is on an embedded system when you have a callback, like interrupt, similar to when the syscall or the systic interrupts the CPU. And so this is designed to be done in this privilege interrupt context, and it will also take into account, for instance, things that if the interrupt itself interrupted a task, it will make sure to recall the scheduler to get that task to continue. Because if you don't do these sorts of calls, then you might go into interrupt context. You've essentially taken one task executing off of the CPU because you've gone into the interrupt context, and you haven't restarted the scheduler in this task in the appropriate manner by not doing it from ISR call. In the FreeRTOS emulator, these from ISR calls are required to use the asynchronous I/O library which exists, which uses software interrupts from the Linux kernel. We probably won't touch on that in this course, as this goes into a bit of sort of an advanced feature, which I don't think we'll have time for in the 2 weeks, but they exist. And so when you see them in the documentation, just so you know what they are, you probably won't need them, so just avoid their use, so that you can avoid problems, because they're also a little more complex from the sort of the implementation and how you use them. On a side note, when it comes to documentation, there is also a lot more features and even a lot more API functions than what I've presented, especially for instance for the queues. There are like a good couple dozen functions that you can use, and they're all quite straightforward. So if you're wanting to do some sort of special thing, or you're looking for sort of an out-of-the-box solution, I mean, go through a couple of the functions in the API reference. There's lots there, and it's all well documented. And also the API that I've been using is at this freertos.org, and so you can just click on the link here. Everything's very well documented, especially sort of like problem-solving things that you'll find in forums, because FreeRTOS is quite widely used, especially in the sort of more like hobby direction, meaning, and then obviously when they have problems, they talk about it on forums, and therefore there's a lot of actual help out there on like Stack Overflow, on the FreeRTOS forums. And so a lot of the time, or pretty much all of the time, your problem will be solved somewhere on the internet already. So have a Google before you have a problem. It's not a really abstract question, abstract field when no one has got experience with it or asked the questions before. There's also this really handy FreeRTOS reference manual, but also super nice PDF is this Mastering the FreeRTOS Real-Time Kernel, sort of a guide, and it's not so much, I mean, it's very good for explaining FreeRTOS, but in it will also do a very good job of explaining sort of just real time as well. So when it comes to studying which sort of schedulers are, mutexes are, and all this sort of thing, I would recommend to maybe give it a quick read. It's not super long, but you can also pick out the relevant sections that are relevant to you, and it will help you to understand the content a little further. So I think now I'll do a quick demonstration of the timers. I won't so much go through the memory management because it's very much the same as what we talked about in the C programming. You just swap out the functions directly. Setting the stack that you want to use is done in the CMake file. It's quite easy to see. FreeRTOS has like a heap variable that's set, and you'll see a number, and you can just change that one and rerun your CMake, and it will change it. So we'll get into the example now.